Hello everyone. Today we are going to explore one of the most fascinating discoveries in modern physics, the photoelectric effect. Have you ever wondered how solar panels produce electricity from sunlight? Or how automatic doors open when you walk by? Well, the answer lies in a mysterious property of light that puzzled scientists for years. It is a phenomena where light can knock electrons out of a metal surface, almost like light is giving them a push. This discovery not only changed the way we think about light, but it also led to the birth of quantum physics, a whole new way of understanding the universe. And guess what? The genius behind this explanation was none other than Albert Einstein, and it even earned him the Nobel Prize in Physics in 1921. So, get ready to dive into the world where particles and waves collide and light behaves in the most unexpected way. Let's uncover the science behind the photoelectric effect. Before we start the photoelectric effect, let's understand Planck's quantum theory, the key idea that led to the concept of the photon. Planck's theory says that the light energy consists of small pockets called photons or quanta. Okay, so each photon carries a specific amount of energy and is given by this equation. Energy of the photon E equal to hf, that is in terms of the frequency, f is the frequency, or another formula E equal to hc by lambda. Lambda is the wavelength of this photon. So I have taken the red photon here, that is the photon coming from the red light. So E is the energy of the photon, SI unit of the energy is joule, h is the Planck's constant, it is around 6.626 10 to the power of minus 34 joule second. Lambda is the wavelength, SI unit is meter, f is the frequency, SI unit is hertz, c is the speed of light, that is 3 times 10 to the power of 8 meter per second. Okay, so red photon having a frequency nearly 4.310 to the power of 14 hertz, whereas the wavelength is around 700 nanometer. Let's calculate the energy of this red photon. E equal to hf formula, so 6.626 times 10 to the power of minus 34 times 4.3 times 10 to the power of 14. So the energy is around 2.85 times 10 to the power of minus 19 joule. This is in the SI unit. Okay, energy of this red photon is in joules. Okay, whenever we are using this formula E equal to hf or E equal to hc by lambda, we get the answer energy in joules. But in atomic and in quantum physics, the joule is very small. So we use more convenient unit, that is the electron volts. So it's very simple converting joule into the electron volt. Just divide the joule, this number, with charge of an electron, which is around 1.6 times 10 to the power of minus 19. So the answer is around E equal to 1.78 electron volts. So this red photon having the energy around 1.78 electron volt. So different photons will have different energies, different frequency, different wavelengths. That is the green photon having different frequency, different wavelength, different energy. The blue photon are like this. So different photons will have different energies, different frequency, different wavelengths. And one more thing, observe here, more is the frequency of the photon, then more is the energy. Direct relationship, the frequency and the energy, direct relationship. Whereas in terms of the wavelength, more is the wavelength of the photon, then less is the energy of the photon. So the wavelength and the energy inversely proportional. Okay, now let's get into photoelectric effect. What is photoelectric effect? So this is the experimental setup, or you can say this is the FET simulation. So we will discuss afterwards. Let's understand what is photoelectric effect in a simple way. Photoelectric effect means the emission of electrons from a metal surface when exposed to light of suitable frequency. Suitable frequency is called the photoelectric effect, and these emitted electrons are called photoelectrons. Observe, look at here. This is the metal surface. So here I have taken the potassium metal. Okay, so the work function of this potassium metal surface or potassium is around 2 electron volt. That work function means the minimum energy required to eject an electron. That's it. So if we supply 2 electron volt energy, then only we can able to remove an electron from this surface. Okay, remember the key area in this is one photon can eject only one electron. So let's take only one photon here. So red photon, let's start with the red photon. So it is having energy around 1.78 electron volt, whereas the work function of this potassium is 2 electron volt. It means the energy of the photon is less than this work function of this metal. So if the energy of the photon is less than the work function of the metal, so this photon unable to eject the electron from this metal surface. That's it. Let's move on to another photon. So this time we have taken a photon from the green light. So it is having energy of 2.25 electron volt, whereas the work function is 2. So now the photon, this photon is having a little more energy. Now it means it can eject the electron from this metal surface. Okay, it is having little more energy. So this energy, little more energy, whatever it is having, so this energy minus the work function, so that is 0.25 electron volt. So that remain in the electron as the kinetic energy. Remain. So this is the photoelectric, Einstein's photoelectric equation we have to use here. So that is energy of the photon E equal to the work function of the metal plus the kinetic energy of the ejected electron, that is the photoelectron. That's it. So here, so the ejected electron here in this case having a kinetic energy of 0.25 electron volts. Okay, once we know the kinetic energy, we can get it the speed of the electron here. So kinetic energy, what is the formula? Half mv square. Okay, so before using the half mv square, we should first convert the electron volt into the joule first, then use the half mv square formula, then we can find the maximum speed of the electron here. In this case it is around 2.96 10 to the power of 5 meter per second. Let's take another photon, so which is having okay, this is the blue photon which is having energy around 2.62 electron volt. Yes, what is the work function of this metal? S2. So it means again this photon also having little more than the work function. Okay, so how much extra it is having? Okay, so 2 electron volt energy is given to eject an electron. Okay, the remaining, that is 0.62, the remaining energy will be with the photoelectron as in the form of kinetic energy. So it means in this case with more speed the motion of the electron, the speed of the electron is more in this case compared to here in this case. So here the speed of the electron is around 4.6 times 10 to the power of 5 meter per second. So we have explained this one by taking only one photon. So one photon can eject only one electron in this case. Okay, more photons can eject the more number of electrons if the energy of the photon is more than the work function of the metal. Okay, now let's discuss in terms of the intensity. Okay, just now we discussed in terms of the frequency. If the photon having the less frequency, so the photoelectrons have the less speed, or you say less kinetic energy. if the frequency of the photon, incident photon, having the more frequency, means more energy it is having, then the ejected photoelectrons have the more kinetic energy. It means more faster it can move. Okay, now let's discuss in terms of the intensity of the radiation. Intensity means you can take it as the number of photons, intensity as the number of photons per second. Okay, so lower intensity, it means that uh, less number of photons, less number of photons per second. Okay, so in the previous case we have, let's assume the whatever the frequency is there of the photon, it is or whatever energy of the photon is there, it is more than the work function of this metal. Okay, it can able to eject the electrons. Okay, then what if lower is the intensity of the radiation, means less number of photons are falling on the surface, so it can emit less number of electrons from the surface. Let's assume 10 is the intensity here, means 10 number of photons are falling here. It means only 10 electrons it can eject from the metal surface. Now let's increase the intensity. Let's say 100 photons. 100 photons are shining the surface, then 100 electrons are coming out of the surface ejecting. So more is the intensity, that is the more number of photons, means more number of photoelectrons. That's it. So here one frequency is related to energy. Okay, kinetic energy of the ejected electrons, speed of the ejected electrons. Another case is intensity. Intensity is related to the photo current, that is the number of electrons. That's it. So intensity, photo current, number of electrons. Okay, here the speed of the photoelectrons. Frequency means related to the kinetic energy or the speed of the. Now let's understand the photoelectric effect with the help of FET simulation. Okay, so what is photoelectric effect? It is the emission of electrons from a metal surface when exposed to light of suitable frequency. These emitted electrons are called the photoelectrons. So this is the FET simulation. So let's understand different the parts of this experiment. So first start with the light, this part. So this is the light. Okay, so light means it is a electromagnetic radiation that consists of photons. So according to Planck's quantum theory, the energy of the photons coming from this light is given by E equal to hf. Okay, next understand the control panel of this light. So here two sliders are given. This is one intensity slider, another one the frequency slider, or you say wavelength of the wavelength slider, or you say energy slider, energy of the photon. Okay, so intensity means here if you keep it in the minimum mode, so less intensity means less number of photons per second. So moving to the right means more intensity we get, that is the more number of photons per second. Okay, we can change in this we can change from 0 to 100. Now let's focus here. So that is the this side infrared region. So in this simulation it is given only infrared to ultraviolet. Infrared means it is the longer wavelength. Longer is the wavelength, lower is the frequency, so lower is the energy of the photon. Okay, so when the slider, when we are sliding it from left to the right, means we are decreasing the wavelength. Decreasing the wavelength means shorter is the wavelength, means higher is the frequency, that is the higher is the energy of the photon. Now finish the control panel. Now come back here. So this part is the metal surface. So from this metal surface our target is to eject the electrons with the help of this radiation, that is the photons. Okay, now different metals have the different work function. So that is the work function means the minimum energy required to eject the electrons. So the photon should satisfy that minimum condition, okay, then only it can eject the electrons. So these are the ejected electrons here, okay. So if the energy of the photon is more than the work function of this metal, then the photons move with the kinetic energy. So the photoelectrons are these electrons are called photoelectrons, and they have the kinetic energy, okay. So all the photoelectrons moves towards the collector end, okay. So now the beauty here in this experiment is to find the kinetic energy, how to find the kinetic energy of the electrons, and how to find the speed of the photon. Yes, here we use the logic here, that is the battery is given here, okay. So with the help of the battery we can find the kinetic energy. So logic is just we apply the reverse potential. So we will discuss what is reverse potential and all, okay. Next, also the current, the electrons are starting from this metal to this collector. So if the flow is continuous, no breaks are there almost. If it is continuous, the circuit will be closed. If the circuit is closed, we get the current in the circuit. So of course that is in milli amperes and nano amperes, okay. So that's it, okay. This current whatever we are getting is with the help of the photoelectrons here, okay. That's it. Let's get into the FET simulation. This is the FET simulation. Yes, let's play with it. So this is the metal target, okay. You can change the metal target from here. If it is zinc, then copper, here observe, here it's changing, then platinum, then so different metal target. At present we are keeping only the sodium. So we can also have some beautiful graphs here. So if you understand more, we can also use the graphs, okay. Now just now we discussed this is the intensity of the light. Let's move the keep the intensity of the light, move the slider, so changing from 0 to 100. So in this case, as the energy of the photon we kept it 850 nanometer, means the energy of this photon, whatever is the photons, are not sufficient or not matching the work function of this metal, okay. So we can also see in terms of the photon also. So let's change the intensity from 0, no photons are coming. Let's make it 10, then 20, 30, 40. What is our observation? More photons we are getting. That's it, okay. Keep it some minimum value, maybe around 20, 30 or whatever, maybe. Let's keep it like this. Now play with this slider, okay. Change the frequency, or you say wavelength, or you say energy of the photon, okay. The photons are coming here, okay. Let's observe what is happening. We are moving from ultraviolet to the red one. It is 750. So still there is no photoelectrons are coming out from the metal surface. So red photon is not sufficient. Then let's increase the frequency, that is decrease the wavelength. Even the yellow no, like this, okay. So green we entered, yes, we got some electrons coming out of the surface here, okay. So it means green photon can able to eject the electrons from this metal surface, because the energy of this green photon is matching, is more than the work function, okay. So what is happening here? Okay, some photons are ejected here. Let's play now. We play with the intensity button, so that is increase the number of photons here, okay. Here see the energy and see the number of photons here. Okay, let's increase the intensity. What is your observation? If we increase the intensity, more photons are falling on the surface. It means more electrons are coming out of the surface. More ejections, that's it. More intensity means more photons, more ejection, that's it. There is no change in the kinetic energy of the photons emitted. So intensity is not connected with the energy of the photons. Okay, bring it back. Now let's change the frequency. Otherwise you can say energy of the photon. Let's increase. Let's keep it around 450. Let's check what is the observation, or let's keep it at, okay, for whatever number you take it. Okay, then what is the observation? We observe that this time the speed is more. Okay, if we increase the energy, that is decrease the wavelength, okay, then the speed of the ejected electrons more. Okay, let's change it. Let's take it to the more energetic ultraviolet. Let's observe here. Then you can see here, with more energy the electrons are emitted. So more energy means more kinetic energy. More energy of the photon, more kinetic energy of the photoelectron. That's it. Now let's understand the stopping potential. Okay, in order to that we need some photo emission here. Okay, for that switch on the bulb. So take it some number. Okay, so electrons are emitted here, photoelectrons are emitted. Okay, so and also photo current is observed 0.071. okay, then what? Here is the battery. So this is the collector. Now the battery is at 0 volt. It means this collector is at the same potential of this emitter. Okay, so here the photo current is some 0.071. Let's make the collector more positive so that it can attract more number of electrons. So let's make it more positive. When we are making the collector more positive, we observe that the speed of these electrons or attraction is more. The speed is more. Okay, we make it more positive, the collector, whereas there is no change in the photo current. So 0.071 is fixed. So this is your observation. So when we are making it more positive, so the graph here 0 to the right side, it is showing the horizontal line. So it is showing the saturation. Even though we make it more positive, the current remains the same. Okay, this is at the intensity, for example, is taken at a fixed intensity. Okay, now make it to 0 again. Now observe. Now the real concept of stopping potential is important for us. From the stopping potential we can find the kinetic energy of the electron, or you can say the speed of the electrons. So here we focus only on the maximum kinetic energy and the maximum speed of the ejected electrons. Okay, let's make it this collector as the negative. So negative means electrons are negative repulsion. Let's repel the electrons by applying the some negative here. What happens when it is made 0.2 negative? Then the current is 0.05. okay, let's make it more negative. Then what happens? The current is reduced further. Next, make it 0.6. again the current is reduced, and also our observation is the speed of these electrons are decreased. Let's make it 0. minus 0.8. okay, so here at this potential, so negative 0.8 potential is applied here at the collector. So none of the electrons is reaching this one. Okay, the repulsion is going on, so that the current is 0, photo current is 0. Where the photo current is 0, that minimum potential is called the stopping potential. So here in this case, okay, the stopping potential for these conditions, okay, so say for example the wavelength or the energy whatever you take, for this one the stopping potential is 0.8 volt. Okay, so let's increase the intensity. Okay, let's make it even. Let's before that, let's make it even negative, negative, negative. Okay, what is happening here? Even when we make more negative, before it was reaching close to that, now it is not at all reaching. So these values we don't want. We want only the minimum voltage which makes the photocurrent 0, that is 0.8 in this case. Okay, let's observe, let's increase. So here you can see the graph, here you can see here, that is minus 0.8 is our stopping potential, okay, where the current is 0. This is the graph. Okay, next observe the intensity. Let's increase the current here, or you can say more current. More current, what is the, let's make it 100. Let's make it 100. Of course more electrons are coming here from this, but more electrons will not change the stopping potential. Okay, let's observe again we study. Let's make it start from 0 volt. Here the intensity is 0, the intensity is 100%, okay, for a given energy of the photon, or you say frequency. So of course here this time you can see the current is more, 0.141 more current we are getting. Okay, so by keeping the frequency constant, we have just increased the intensity. When the intensity is increased, the current, the saturation current value is increased. Okay, now let's stop these electrons to reach this collector. Okay, one thing, let's see the saturation current. For that, increase the potential here, make it more positive. The collector side, there is no change, so 0.141 is the saturation current. Now let's make it 0 and apply the negative potential slowly. Negative potential slowly, yes, at minus 0.2 current is there, but it is decreased, minus 0.4, minus 0.6, still some current is there, minus 0.8. Yes, so it means that even though we increase the intensity, even though we increase the current, but the stopping potential is the same. Stopping potential does not depend on the intensity. That's it. Stopping potential does not depend on the intensity. Whatever intensity of the photons we take it, stopping potential will not change. It remains the same. This is the observation. Now let's study the photoelectric effect different way, or you say stopping potential in different way. Now we are keeping the intensity fixed, okay, and we will change the energy of the photon, or you say frequency of the photon. Let's observe here. The previously just now we did for a given intensity at 50% of the intensity. Okay, 50% is not important here. Okay, just for understanding. Okay, for this frequency or for this wavelength, we got the current is 0.071. Okay, to make this current 0, we applied the stopping potential. You remember, I think minus 0.8. So note down, for 400 nanometers wavelength, minus 0.8. Okay, now take it back to 0 again and observe what happens when the frequency is increased. Let's make it 300 around. Okay, now observe whether now this time the current is 0.275. let's make it negative, make the current 0. So minus 0.8 is not sufficient here. Now we need to give the more. Yes, it is minus 1.8 now. Okay, to make the current 0, it means when the energy of the photon increases, the kinetic energy of the photoelectrons increases. So in order to stop these electrons on reaching the collector, that is to make the current 0, we have to apply the more stopping potential. Let's make it more. Okay, let's bring back to the 0 again here. Obviously when you increase the frequency, then the energy of the photons will increases. Okay, now this time with more energy, more speed, it is reaching the collector. Okay, so in order to stop them, we have to give the more reverse potential, stopping potential. Okay, so this time we have even minus 3 is not sufficient. Yes, it is around 4 volts. So what we understood, so at this reverse wall, even the fastest electron is unable to reach the collector, bouncing back. So finally our conclusion is that at a given intensity, okay, then if we increase the energy of the photon, or you say frequency of the photon, the speed or the energy of the photon increases. In that, to stop them to reach the collector, we need to give the more stopping potential, reverse potential. That's it. Let's summarize our observations in photoelectric effect. Our first observation is electrons are emitted immediately. As soon as the light of a certain frequency or higher shines on the metal, electrons come out of instantaneously. That is, there is no delay. Second observation is there is a minimum frequency required. Below a certain frequency, no electrons are emitted, even if the light is very intense. This frequency is called the threshold frequency, or you say cut-off frequency. Third one, kinetic energy of electrons depends only on the frequency, not on the intensity of radiation. Higher is the frequency, higher is the energy of the photons, that is the more energetic electrons are emitted. That is, the faster electrons will be ejected. Increasing the intensity does not increase the speed of the electrons. Only increasing the intensity will increase their number. That's it. Number of electrons depends only on the intensity. More intense light means more photons, that is the more electrons are emitted if the frequency is above threshold. This is the whole summary whatever we studied. Okay, this is the graphical analysis, the same thing what we observed. When the frequency is fixed above the threshold, so more photons will give you more electrons, that is the more photocurrent. That's it. Higher is the intensity of the radiation, higher is the photocurrent. That's it. Higher is the photocurrent, but there is no change in the stopping potential. Okay, another observation, suppose for a given intensity, if the frequency of the light increases, the photon energy increases. Consequently, electrons are emitted with more kinetic energy. So the stopping potential increases. In order to stop these faster electrons, the graphs looks like this. The last one, the graphical representation, that is, so different materials have different work functions, or you say different the cutoff or the threshold frequency. So this is metal 1, so here is the cutoff frequency, or you say threshold frequency here, and this is the work function of that metal 1. The second one, metal 2, this is the cutoff frequency and this is the work function. So whatever it may be, so metal 1 and metal 2, they are the graphs are parallel. It means they have the same slope. So for kinetic energy and the frequency, the slope of the graphs are the Planck's constant h. That's it. Now let's start solving some numerical problems. So before solving these numerical problems, let's recall the formulas. metal surface. So metal surface has work function. We represent the work function with letter phi. Okay, the formula for this one is hf, the threshold frequency or cutoff frequency. We can also write in terms of the lambda, that is hc by the lambda, cutoff frequency. This one work function. Next, about the photon. Photon has the energy that is equal to E, which is equal to hf is the frequency, or another formula that is E equal to hc by lambda. Okay, let's come to the electron now, that is the photoelectron in this case. So photoelectron has kinetic energy which is equal to half mv square. This is the formula. Now it has multiple formulas, so that is the stopping potential. We come here, stopping potential formula is, we represent stopping potential with letter either Vs or V0, it's up to you. So Vs equal to kinetic energy of the electron divided by charge of an electron. Okay, next one, your Einstein's photoelectric equation. Photoelectric equation which combine all of them, that is this, this and this. Okay, all of them here in this equation. That is, the energy of the photon is equal to the work function of the metal plus the kinetic energy of the electron. Okay, so now we can also write one more formula, that is the speed, the maximum speed of the electron, that is V max equal to, that is in terms of the stopping potential, root of 2e, the stopping potential here, don't get confused, this is the stopping potential, divided by the mass of the electron. This is the speed, my dear. That's it. So we have to remember these formulas. Okay, with these formulas we can solve any problem. Come on, let's start. A sodium surface is illuminated with a light of wavelength lambda is given to you 0.3 micro. 0.3 micro, micro means 10 to the power of minus 6 meter. The work function of the sodium, that is phi. Okay, so whenever we are going to use the formulas, electron volt is not okay, then convert it into the joule. So 2.46 multiplied with 1.6 into 10 to the power of minus 19, so which is equal to, we have to use the calculator. Okay, we will use the calculator. I don't have now, right now. Next, the answer we get it in the joule. Okay, let's calculate the energy of the each photon. Energy of the photon, the first one, E equal to hf is the formula. H is the Planck's constant, that is 6.63, around 6.63 or 6.626, it's up to you, time 10 to the power of minus 34 into the frequency. Oh, so hf is not useful, this formula, so hc by lambda we will use, that is c is the speed of the light, 3 into 10 to the power of 8 by the given lambda, that is equal to 0.3 times 10 to the power of minus 6. Let's use the calculator and find the energy. So we got the answer 6.63 times 10 to the power of minus 19. This is in the joule. That's it. Okay. In order to do other problems, so let's convert into the electron volts, because the electron volts for the photons we usually represent electron volt. So whatever you get it, 6.63 times 10 to the power of minus 19 by 1.6 into 10 to the power of minus 19 will give you the electron volt. The answer is around 4.14 electron volt, the B bit. Find the maximum kinetic energy of the ejected electrons. Maximum kinetic energy of the electrons. Maximum kinetic energy formula is half mv square is the formula. Okay, this is not the smart way. Use another formula for the from the Einstein photoelectric equation we can find the maximum kinetic energy. The formula is maximum kinetic energy Ke max equal to the energy of the photon E minus, from here we are doing E minus phi, so which is equal to energy of the photon. Just now we got 4.14 electron volt minus the work function is 2.46 electron volt, which is equal to around 1.68 electron volt. This is the maximum kinetic energy of the photoelectrons. The last one, what is the cutoff wavelength of the sodium? Cutoff wavelength. So cutoff wavelength means it is related to the work function here. So work function means, what's the formula for the work function? Work function equal to hf naught or hc by lambda naught. So let's use hc by lambda naught. Okay, from this we can find the lambda naught, that is equal to hc by the phi. So which is equal to, h value is 6.63 times 10 to the power of minus 34. The C is 3 into 10 to the power of 8 divided by the work function. Work function, it is not okay. It should not be. Whenever we are using these type of formulas only SI units. So 2.46 times 1.6 into 10 to the power of minus 19. So the final answer for the cutoff wavelength is 4.8 times 10 to the power of minus 7 meters. Okay, these are the answers. So you have to remember these formulas to solve any problem related to photoelectric effect. Come, let's do problem number 2. What minimum frequency light will eject the photoelectrons from the copper surface? A bit. Second one, okay, so first we have to know the copper work function. Without the work function of the copper, we don't know. We cannot solve this problem. Let us assume the copper has the work function is around 4.5, 4.6, 4.7, different values are there. Let's take with 4.7 electron volt. This is the work function of the copper. Now we can calculate the minimum frequency. So work function formula, I told you there are two formulas are there, hf naught, another formula is hc by lambda naught. So minimum frequency means the f naught we have to calculate. So f naught equal to the work function by h. So work function we are taking, whenever we are using this formula, only SI unit, joule we need. So electron volt to joule, that is we have to multiply with 1.6 times 10 to the power of minus 19. Don't forget the Planck's constant is 6.63 times 10 to the power of minus 34. Use the calculator and find the answer. So it is around 1.13 times 10 to the power of 15 Hz. The B problem number B. If this frequency is tripled, means 3 times. If this frequency is tripled, find the maximum kinetic energy in the electron volt of the resulting photoelectrons. Okay. Find the maximum kinetic energy. So formula V kinetic energy equal to half mv square is the formula. So from this it's very difficult, we cannot directly easily we can calculate. So let's use the Einstein photoelectric equation, that is kinetic energy we can get it by the energy of the photon minus the work function of the metal. Okay, so it's given that the frequency of the photon is tripled. The frequency, the formula is hf is the frequency, but they told the frequency is tripled, so h into the previous f naught. Okay, so 3f0 minus 5. Okay, let's substitute all the numbers there. 6.63 times 10 to the power of minus 34 times 3 times 1.13 times 10 to the power of 15. Okay, this much is the energy of the photon minus the work function. So work function should be in, whenever we are using the formula, it should be in joule. So work function of the copper is 4.7 time, that is 1.6 times 10 to the power minus 19. Okay, so use the calculator. The answer is 1.5 times 10 to the power of minus 18 joules. Again they asked us to find in the electron volts. So joule to electron volts, very easy, just divide the joule with 1.6 into 10 to the power of minus 19. This much is the electron volt. So the answer is around 9.4 electron volt. Next problem. Electrons are ejected from a metallic surface with a speed ranging up to 4.6 times 10 to the power of 5 meter per second when light with a wavelength of lambda equal to 625 nanometer is used. What is the work function of the surface? Let's recall the formulas we know about the work function. Work function, the formula is, one formula is hf naught, another formula is hc by lambda naught. Okay, so based on the given information, we don't know. So let's use, instead of this formula, let's use the Einstein's photoelectric equation, that is the energy of the photon equal to the work function of the metal plus the kinetic energy of the electron. Remember, this is your energy of the photon and this is the work function of the metal. This is the kinetic energy of the photoelectron. Okay, so from this we can write it as the work function equal to E minus kinetic energy. So energy of the photon, the formula is hf, kinetic energy, the formula is half mv square. So energy of the photon. Okay, so energy of the photon, when a light means the photon, remember the photon. So instead of hf, let's use hc by lambda, that is better. hc by lambda here. Okay, so h is 6.63 times 10 to the power of minus 34. The speed of the light is 3 into 10 to the power of 8 by the wavelength of the light, that is 625 nano. Nano means 10 to the power of minus 9. So this is all for the energy of the photon. Now for the electron, the formula is half mv square. Half the mass of the electron, remember, without this we cannot solve this problem. So 9.1 times 10 to the power of minus 31. This is the mass of the electron times the speed of the electron is given 4.6 times 10 to the power of 5. The speed whole square. Okay, so this minus this, let's plug in these values in the calculator. Our answer is around 2.2 times 10 to the power of minus 19 joule. Divide the joule with charge of an electron, so our answer is 1.4 electron volt. Next one, what is the cutoff frequency? What is the cutoff frequency of this surface, metal surface? Okay, so the B bit. What is the cutoff frequency of this surface? Cutoff frequency means, now we will use this formula. Okay, work function equal to hf naught. Therefore the cutoff frequency or the threshold frequency equal to work function divided by the h. So work function, just now we need the joules only. Whenever we use the formula, we joules only we use. That is 2.2 times 10 to the power of minus 19 divided by 6.63 times 10 to the power of minus 34. So the frequency is around 3.3 times 10 to the power of 14 hertz. Problems will be very easy only when you remember the basic formulas. Okay, last problem now. Molybdenum has a work function of 4.2 electron volt. Electron volt is not the SI unit, so 4.2 times 1.6 into 10 to the power of minus 19. This is the joule. Okay, find the cutoff wavelength and the threshold frequency of the for the photoelectric effect. So threshold frequency, threshold wavelength, so it is all related to work function. So formula is hf naught, one formula, another formula is hc by lambda naught. So we will use the cutoff wavelength. Cutoff wavelength, what is the formula? Lambda naught equal to hc over the work function. So which is equal to h is 6.63 times 10 to the power of minus 34 times c is the speed of light, 3 times 10 to the power of 8 meter per second over the work function in the joule, that is 4.2 times 1.6 into 10 to the power of minus 19. So the answer is around 2.96 10 to the power of minus 7 meter. Now the B bit. Now what to calculate the frequency? So frequency, so from this the frequency, the formula is cutoff frequency equal to work function over by the Planck's constant. Work function in the joule, that is 4.2 times 1.6 into 10 to the power of minus 19 over the Planck's constant 6.63 times 10 to the power of minus 34. The answer is 1.01 times 10 to the power of 15 hertz. That's it. Thank you very much.